Hi there, this is a short service update on my GPIB to USB interface on the left, which I made for my Solartron 7150 Plus multimeter. The 7150 Plus is a 6.5 digit multimeter, and despite being from the early 90s, it is still highly accurate and relatively easy to restore. I put a link to my restoration of this multimeter in the description below. The 7150 Plus has a proper GPIB interface for remote control. The general purpose interface bus, also known as IEEE 488, is still common in a lot of high-end measuring equipment, but of course many devices now have additional USB or LAN interfaces. Commercial GPIB to USB adapters are outrageously expensive, to the tune of several hundreds of pounds. So right after getting the 7150 Plus working, I made my own using an Arduino Nano, which is another video I link in below. Now, I had not used the GPIB interface for a while, but when I wanted to use it with my current DPS control project, it didn't work anymore. I spare you many hours of troubleshooting because GPIB is a parallel bus with 16 lines, all connected via termination resistors to the Arduino Nano digital I/O and analog I/O pins. They are standard GPIB interface driver chips, but they are very expensive, hence the cheap resistor solution. In the end, I narrowed it down to the software in the Arduino Nano that wasn't working correctly anymore. Somehow the program had been corrupted. An upload of the same code fixed the problem and everything was fine until the next day when it had stopped working again. In the early days I had the Solartron sitting on my bench and connected to the GPIB only when I needed it, but since then I had moved it into a rack, and since getting to the GPIB connector at the back is somewhat awkward, I had left a converter permanently attached to the 7150 Plus. But here's the crucial point, I had not connected it to a USB port. By chance, I had the unit open and connected it to the powered 7150 Plus, but disconnected from the USB, and I noticed some strange effects on the Arduino Nano. The green power light would sometimes come on weakly, and the L LED might also come on occasionally. Clearly the board was receiving some stray power from the GPIB bus, but not enough to work properly. The top part shows the principle of the termination. Just imagine this times 16. It is clear that in the absence of 5V power from the USB, the Arduino somehow gets enough power through the GPIB, through its I/O lines or through this connection, to do something that will eventually corrupt the flash memory. What it does and how long that takes depends, I guess, on the state on the GPIB bus lines when the USB power is removed. My first attempt at fixing was a diode in the 5V, but that didn't help. In the end I resorted to a switch in the ground connection, and that put an end to it. The only problem is to remember to flick the switch before removing USB power. That solution kind of works, but it's clearly not very satisfactory. Let me demonstrate. Here you see into the GPIB converter box while it is connected to both GPIB bus and the USB. Watch what happens when I remove the USB plug from the Arduino. It's a bit tricky to see, but something is clearly still going on down there. The switch stops it, but even in this short test it was too late. The program on the Arduino was already corrupted. I examined the ATmega328 datasheet, and it does have a brownout detection or BOD capability. If enabled using the extended fuse byte, the chip monitors the level of its supply voltage and initiates a reset if it falls below the program value. I measured the stray supply voltage to be slightly above 2.2 volts, so even a BOD level of 5 or 2.7 volts should detect this, but to be safe, a level of 4 or 4.3 volts would be better. Once BOD is triggered, the processor will stay reset while the voltage remains below the trigger level. So this sounds like a solution to avoid memory corruption. The only problem, it turns out, was that the extended fuse byte was set to hex FF, which means all bits set, and that means brownout detection was disabled. How to change the extended fuse byte in an Arduino Nano? Now you can't use the Arduino bootloader to set fuses on its own chip. You need to use the in-socket serial programming socket for that, which means you either need a second Arduino to act as a programmer or some other suitable ICSP programmer. Luckily I have a USB ASP programmer which is supported by the Arduino IDE, so that wasn't a problem until AVR-Dude, the program to run the USB ASP programmer, refused to do anything with my Arduino Nano because the device signatures did not match. It turned out my cheap Chinese clone Arduino uses an ATmega 328PB chip and not a 328P chip, which is the only thing the Arduino IDE supports and commands AVR-Dude to check against. The 328PB is a slightly more advanced version of the 328P and crucially has a different signature. So AVR-Dude was set up by the Arduino IDE to program a 328P chip but found the signature of a 328PB chip and stopped. There are ways to override this check, but in the end I found a much simpler solution than messing around with configuration files. I simply copied the failed command from the upload window in the Arduino IDE and pasted it into a terminal window. Then it was as simple as adding a B at the end of the 328P and press return, and the E fuse was changed from FF to F4. Since that process erases the memory, you lose the bootloader and your program. So I used the same method to upload the bootloader, and in that process also upgraded the old bootloader that was on the chip when I bought it to the new bootloader. Once that was done, I removed the in-circuit programmer and uploaded the GPIB-to-USB sketch from the Arduino IDE using the normal way through the USB cable and the freshly installed bootloader. Here's another test with the BOD enabled at 4.3 volts. With the USB power removed but the GPIB still connected, the voltage drops, as you can see by the dimmer LED. The chip is disabled and stays inactive. But as soon as the USB power is restored, everything is back to normal. Well, I think the trick of enabling brownout detection has hopefully solved this problem for good. Thanks for watching.